There is something remarkable about seeing Mars from a distance. The red planet hangs in the darkness, with two small companions trailing along in their ancient orbits. The first time I understood that Mars had moons, genuinely understood it rather than simply knowing the fact, the planet felt different to me somehow. These are not grand moons like our own, not bright disks that dominate the night sky of their world with reflected light and gravitational presence. They are small and dark and strange, more like captured wanderers than true children of the planet. They circle endlessly. The larger of the two is Phobos, and tonight we approach it first as the spacecraft drifts through the darkness of the Mars system towards something solid. From a distance, Phobos appears as little more than a dim point against the stars, barely distinguishable from the background of space surrounding it. As the distance closes, however, something begins to resolve. A shape that is clearly not spherical, clearly not the smooth round form we expect from moons. The outline emerges gradually, lumpy and irregular, stretched longer in one direction than the other, battered by forces that shaped it long ago. You are listening to the Drowsy Astronaut, and tonight we are visiting two of the strangest moons in our solar system together. This is a slow journey designed for late-night listening, for drifting along with the words, while the mind relaxes into the darkness between the stars. If this helps you unwind, consider leaving a like or subscribing, and let us know in the comments where you are listening from around the world tonight. We have all the time we need to explore these ancient worlds, so settle in and let the journey unfold at whatever pace feels right. The shape of Phobos becomes clearer with each passing hour of approach, the irregular contours sharpening against the black backdrop of space behind it. Early observers compared this moon to a potato, and the comparison feels apt as the full form reveals itself in the growing light. The longest dimension stretches about 27 kilometers, while the shortest spans only about 18 kilometers across the narrower axis of the body. This is not a world that gravity has pulled into a sphere. Phobos is too small for that. Its own self-gravity too weak to overcome the rigidity of the rock that composes it. The surface appears dark, extraordinarily dark. One of the darkest surfaces found on any object in the entire solar system that we have examined closely. Phobos reflects only about 7% of the light that strikes it. Darker than charcoal, darker than asphalt, on a rainy night in a city. This darkness gives the moon a brooding quality as it grows larger in the view, a sense of ancient patience accumulated over billions of years of silent orbit. The color is not quite black, but rather a very dark gray, shading toward reddish-brown in places where the light catches the surface at certain angles. Craters cover the surface densely, impacts accumulated over the long history of this small world, circling Mars in its lonely path. Some craters are small, mere pockmarks a few meters across, while others span hundreds of meters and show clear, bowl-shaped depressions with raised rims. The craters overlap in places, younger impacts having struck within the boundaries of older ones, creating complex patterns that speak of bombardment continuing across vast stretches of time. Every solid surface in the solar system collects craters, but Phobos has collected them with particular density, given its small size and long exposure. One crater dominates all others, visible even from this distance as a massive depression that spans nearly 1/3 of the Moon's entire width across the surface. This is Stickney, the great wound that nearly shattered Phobos when it formed, and we will explore it more closely soon in our journey forward. For now, its presence simply marks the geography, a landmark that helps orient the view as the irregular Moon rotates slowly in its orbit. The crater's rim catches the light differently than the surrounding terrain, creating a subtle variation in brightness across the visible face. Strange linear features cross portions of the surface, visible as the approach continues, and resolution improves with decreasing distance between spacecraft and Moon. These are grooves, roughly parallel trenches that stretch for many kilometers across the terrain, in patterns that seem too organized to be random craters. Scientists have debated their origin for decades, since spacecraft first revealed them, and we will explore the mystery they represent later in our journey tonight. For now, they simply add to the sense that this is a world with stories to tell, patterns to understand, features that invite closer examination. The texture of the surface becomes visible as the final kilometers of approach unfold slowly in the darkness between spacecraft and Moon. What appeared smooth from greater distance resolves into rough terrain, covered everywhere with a layer of broken and pulverized rock called regolith. This grey blanket of debris has accumulated through billions of years of small impacts, each collision grinding the surface material into progressively finer particles over time. The regolith may extend many meters deep in some places, accumulated so slowly that no single event was noticeable, yet the total depth grew substantial. Boulders dot the surface here and there, rocks too large to have been fully buried by the finer material that surrounds them on the ancient terrain. Some of these boulders are surprisingly large, the biggest perhaps 85 meters across, sitting on the surface like monuments to the violence that ejected them from somewhere else. They may have been thrown out of craters during impacts and simply landed where we now see them, never sinking far into the soft regolith below. In the weak gravity of this small world, even large rocks can travel far before coming to rest on the surface. The approach has brought us close enough now that the curve of Phobos fills much of the visible field, the horizon of this small world appearing quite close at any point on the surface below. This is a world so small that you could walk around its entire circumference in a single long day, if walking were possible in its strange environment. The surface area is roughly equivalent to a modest Earth city, small enough to feel comprehensible, yet large enough to contain genuine geography worth exploring at leisure. Every feature we have glimpsed invites closer examination. The lighting changes as Phobos rotates, and the spacecraft's position shifts relative to the Sun and the small Moon's orientation in space. Shadows lengthen and shorten, craters revealing their depth through the contrast between illuminated and dark regions within their bowls below the rims. The grooves stand out more clearly when the sun angle is low, their shallow depth becoming visible through shadow patterns that cross the surface terrain. This interplay of light and shadow will accompany all our exploration here. Mars itself hangs in the background throughout this approach, the red planet, enormous from this perspective, dominating the view in a way that Earth never experiences from its own moon. Phobos orbits remarkably close to Mars, closer than any other moon orbits its planet anywhere in the solar system that we know of currently. The planet fills a huge portion of the sky from Phobos' surface, a constant presence that makes the relationship between world and moon feel intimate and immediate somehow. We will explore that relationship and its consequences later tonight. The spacecraft settles into a position where Phobos fills the primary view, the ancient surface waiting to be examined in detail over the coming hours of exploration. This small world has circled Mars for billions of years, patient and dark, collecting craters and waiting for someone to come close enough to really look at it. The Voyager spacecraft flew past in 1977, sending back the first detailed images of this strange moon, and later missions have added to our knowledge, piece by piece, over decades. Now we add our own examination to that history. The first impression is of age, of patience, of a world that has existed in this state for longer than complex life has walked on Earth, or swum in its oceans. Phobos does not change quickly. The processes that shape it operate on timescales that dwarf human civilization entirely, and make even geological eras seem brief. Yet change does happen here. Slowly, impacts still occurring, the surface still evolving, through processes we are only beginning to understand fully even now. This is a world with a history and a future, however strange both may be. The darkness of the surface seems to absorb light rather than reflect it, giving Phobos a quality different from the bright moons we might expect to see orbiting other worlds. This darkness tells us something about the material that composes this moon, possibly similar to certain types of asteroids found in the outer reaches of the asteroid belt between Mars and Jupiter. The connection between Phobos and the asteroids will become important later when we consider where this moon originally came from long ago in solar system history. For now, the darkness simply characterizes the visual experience of this place. We have arrived at Phobos, the larger of Mars's two moons, and the exploration can begin in earnest now that the approach is complete. But another moon waits farther out, smaller and smoother, orbiting at a greater distance from the red planet that holds them both in gravitational embrace. Before we dive deeper into Phobos' most dramatic features, we should glimpse this companion as well, this other small world that shares the Mars system with its larger sibling. The two moons together tell a story that neither can tell alone. The spacecraft turns now, orienting toward a more distant target as we travel outward from Mars to find the second of its two small moons waiting in its separate orbit. Deimos is smaller than Phobos, orbiting much farther from Mars, and the journey to reach it takes us through empty space that seems quieter than the region closer to the planet somehow. The darkness here is the same darkness found everywhere in deep space, but something about the greater distance creates a sense of isolation, of traveling towards something lonely and remote, from even the modest company of its sibling moon behind us. Deimos waits ahead. The first glimpse of Deimos comes as a small point of light against the background stars, barely distinguishable from the stellar background without knowing exactly where to look for it precisely. The moon is so dark, reflecting only about 7% of incoming light, like its sibling, that it does not stand out until the spacecraft draws close enough for its disk to begin resolving into something more than a dimensionless point of reflected sunlight. Gradually, almost reluctantly, Deimos reveals itself as the distance continues to close. The shape that emerges differs from Phobos in subtle but noticeable ways that become apparent as the moon grows larger in the field of view. Deimos is also irregular, also elongated rather than spherical, also battered by a history of impacts accumulated across vast stretches of solar system time. But where Phobos seemed rough and aggressive in its irregularity, Deimos appears somehow gentler, its contours softer, its surface less dramatically scarred by the features that marked its larger companion so prominently. The difference invites explanation. The dimensions of Deimos are modest even compared to Phobos, which itself is already a small world by any standard of measurement used for celestial bodies. This smaller moon measures only about 15 by 12 by 11 kilometers across its various axes, roughly half the size of Phobos in each direction. The entire moon could fit within the boundaries of a moderately sized Earth city, small enough that a determined walker could explore most of its surface in a single day of hiking. Yet, it remains a world unto itself. The surface appears smoother than Phobos as details begin to resolve through the improving view with decreasing distance between observer and moon. Craters exist here too, of course. No solid surface in the solar system escapes the bombardment that marks everything exposed to space over billions of years. But these craters seem softened somehow, their edges less sharp, their rims lower and more rounded than equivalent features on Phobos might appear. The surface looks almost gentle by comparison. The smoothness is not an illusion created by distance or lighting conditions playing tricks on observation and perception of surface detail. Deimos is genuinely covered in a thicker layer of regolith than Phobos, fine material that has accumulated deeply enough to partially fill and soften the features that would otherwise stand out more sharply. The blanket of pulverized rock has accumulated over billions of years, settling into low areas, filling crater bowls, rounding the sharp edges that impacts would normally create on exposed surfaces. Time has smoothed this world. The color matches Phobos closely, the same dark gray to reddish brown that characterizes both of Mars's small companions in their separate orbits. This similarity in coloring suggests a similar composition, similar materials making up both moons, despite their differences in size and surface texture and orbital characteristics. Whatever processes created these moons, whatever history brought them to orbit Mars, the materials that compose them appear to share a common origin, or at least common chemical characteristics, detectable through observation. Craters remain the dominant surface features, despite the smoothing effect of the thick regolith layer covering everything below a certain size threshold. Only 2 craters on Deimos have been given official names, and both honor writers who imagined Martian moons long before anyone actually discovered them with telescopes. Swift Crater, about 1 kilometer across, commemorates Jonathan Swift, who described 2 Martian moons in Gulliver's Travels, published in 1726, more than a century and a half before Asaph Hall actually found them. Voltaire Crater honors the French writer who mentioned Martian moons in his story, Micromagus, in 1752. The naming of these craters connects Deimos to human imagination in a way that feels appropriate for such a distant and little-known world orbiting silently around Mars. Writers imagined these moons into existence through fiction, guessing that Mars might have companions long before telescopes were powerful enough to reveal them directly. When Hall finally spotted both moons in August of 1877, using the 26-inch refractor at the United States Naval Observatory, he was confirming what storytellers had suspected might be true for generations. Science and imagination had converged. The approach continues as these thoughts unfold, the surface of Deimos growing larger and more detailed with each passing hour of the slow journey toward this small world. The texture becomes visible at closer range, the regolith blanket revealing itself as a covering of fine particles that have softened everything they touch across the visible terrain. The material looks almost dusty from this perspective, as if a thin snow had fallen and settled into every low point, muting the landscape into something quieter than it might otherwise appear naturally. The comparison is not quite right, but it captures something of the visual impression. No grooves cross the surface of Deimos, as they do on Phobos, no mysterious parallel trenches stretching for kilometers across the terrain, with their puzzling regularity. Whatever process created those features on the larger moon either did not operate here or did not leave visible traces that have survived to be observed by spacecraft cameras in modern times. The absence is notable precisely because the grooves are so prominent on Phobos. The difference demands explanation, though none is certain yet. The two moons share much, but not everything. The orbital distance of Deimos from Mars is roughly 4 times greater than the orbital distance of Phobos, placing this smaller moon much farther from the planet it circles endlessly. From Deimos, Mars would appear smaller in the sky, still impressive, but not the overwhelming presence it becomes from the surface of Phobos, where the planet fills enormous portions of the visible hemisphere. The greater distance creates a different relationship between moon and planet, a more distant companionship that affects everything about the orbital dynamics we will explore later tonight. The spacecraft settles into observation position, Deimos filling the view as the approach phase concludes, and the detailed examination can begin at a more leisurely pace. This small world has been waiting here for billions of years, orbiting Mars with patience that exceeds any human conception of time or duration. The surface shows its age in the softened craters, the thick regolith, the quiet accumulation of dust that has muted the violence of ancient impacts into something almost peaceful now. Deimos has had time to settle. The impression of gentleness persists as the examination continues, each new detail confirming that this moon possesses a different character than its larger sibling, orbiting closer to Mars. Where Phobos seemed scarred and dramatic, Deimos seems patient and calm, its surface recording the same history of bombardment, but in softer tones, less harsh contrasts, more subtle variations. The difference is real, even if the underlying materials and origins may be similar or identical for both small worlds circling the red planet together. 2 moons, 2 characters, 2 separate worlds sharing the same planetary system in the darkness beyond the asteroid belt, where Mars traces its orbital path around the Sun. Having now glimpsed both companions, we can begin the deeper exploration that this journey promises, starting with the most dramatic feature on either moon. The enormous crater that nearly destroyed Phobos when an ancient impact carved it into the small world's surface long ago. Stickney awaits our attention. The view shifts as the spacecraft reorients for the return to Phobos, the smaller Deimos falling away behind us as the larger moon grows ahead once more against the background of stars and the red bulk of Mars itself. We will return to Deimos later for more thorough exploration of its gentler terrain. But first, the dramatic features of Phobos demand attention and careful examination over the coming hours of our shared journey. The great wound in Phobos' surface has stories to tell about violence and survival, and the forces that have shaped this strange, small world across billions of years of solar system history. The crater called Stickney dominates one hemisphere of Phobos, a wound so large relative to the moon's small size that the impact which created it must have been extraordinarily violent in its ancient occurrence. The dimensions are striking when considered against the scale of the body they mark. Stickney spans approximately 9 kilometers across, while Phobos itself measures only about 27 kilometers at its longest dimension from end to end. This means the crater occupies roughly 1/3 of the moon's entire width, a proportion that would be catastrophic on any larger world, but here represents survival against remarkable odds. The approach to Stickney reveals the crater's form gradually, the circular depression becoming more clearly defined as the distance closes and the lighting conditions allow the feature to reveal itself fully against the surrounding terrain. The rim stands raised above the surrounding surface, material piled up by the force of the impact that excavated this enormous bowl from the body of the moon long ago. The walls slope downward from the rim toward the floor below, steep enough to be dramatic, but not quite vertical, carved by an event that happened billions of years in the past. The floor of Stickney lies several kilometers below the rim level, deep enough that standing at the bottom would place the horizon of this already small world quite close around the observer in every direction. The floor is not smooth, but rather covered with debris that has accumulated since the impact. Smaller craters that have formed within the larger crater's boundaries, and features that speak of continued geological activity even after the original violence had subsided into the past. Craters within craters tell stories of layered history. One smaller crater sits prominently within Stickney's boundaries, a feature named Limtok that measures about 2 kilometers across. A wound within a wound marking successive impacts at the same general location on this battered moon. Limtok formed later than Stickney, obviously striking into the floor of the larger crater rather than the original undisturbed surface that existed before the Great Impact. The relationship between these nested features helps establish the sequence of events that shaped this region of Phobos across time. The naming of Stickney honors Angeline Stickney Hall, the wife of the astronomer Asaph Hall, who discovered both Martian moons in August of 1877 using the telescope at the Naval Observatory in Washington. Angeline encouraged her husband to continue his search for Martian moons when he was ready to give up, and without her support, the discovery might have been delayed or made by someone else entirely. Her name on this dramatic feature connects the human story of discovery to the geological violence that shaped the moon long before any human knew it existed. The impact that created Stickney must have been powerful enough to come close to shattering Phobos entirely, breaking the small moon into fragments that might have spread along its orbit around Mars. Scientists have calculated that the impacting body was probably traveling at several kilometers per second, striking Phobos with enough energy to excavate millions of cubic meters of material and send shockwaves propagating through the entire body of the moon. The survival of Phobos as a coherent object after this event was not guaranteed. The excavation of Stickney threw material outward in all directions, some of it escaping Phobos entirely and some falling back to coat the surrounding terrain with a layer of ejected debris called ejecta. This material is visible as rays extending outward from the crater rim, subtle variations in surface brightness and texture that mark the paths of material thrown out during the explosive moment of impact long ago. The rays have faded over time as subsequent impacts and other surface processes have mixed the ejecta with underlying materials. The walls of Stickney reveal layering in some locations, hints that the interior of Phobos is not uniform, but rather composed of materials with different properties at different depths below the surface. This layering might reflect the original formation of the moon. Materials accreted in sequence during the early solar system, or it might represent later modifications through impact processing and other geological activity over billions of years. The crater walls serve as windows into the interior. The scale of Stickney becomes more impressive when compared to features on more familiar worlds that listeners might know from Earth experience or general knowledge. If Stickney existed on Earth, the crater would be large enough to swallow a major metropolitan area entirely within its bowl-shaped depression below the surface. The city of London or New York could fit within Stickney's boundaries with room to spare around the edges. Yet this enormous feature exists on a moon small enough to drive around in a few hours if roads existed on its airless surface. The relationship between crater size and body size matters for understanding what the Stickney impact meant for Phobos as a coherent object continuing to exist after the event. A crater this proportionately large on Earth would represent an extinction-level event, an impact capable of sterilizing the planet and reshaping global geography dramatically. On Phobos, the impact came close to destroying the moon entirely, and some scientists believe the grooves visible elsewhere on the surface may have formed as the moon nearly cracked apart from the shock. Standing at the rim of Stickney and looking down into the crater bowl, the view would encompass a depression large enough to feel like genuine geography rather than merely a surface feature to walk past quickly. The far rim would be distinctly distant, several kilometers away across the crater floor, the curve of the small moon's surface making the opposite wall appear to rise at an angle against the star-filled sky above. This would be a place to explore for hours, not minutes, despite Phobos's overall modest scale. The floor of the crater has accumulated its own history since the original impact carved this space from the body of the moon in that ancient, violent moment. Smaller impacts have pocked the floor with craters of various sizes, each one adding to the record of bombardment that continues even now across all exposed surfaces in the solar system. Dust has settled, regolith has formed. The sharp features of the original impact have softened slightly under the patient work of cosmic erosion operating over billions of years. The temperature variations across Stickney would be dramatic, the crater floor receiving different amounts of sunlight depending on the sun's angle and the position of Phobos in its orbit around Mars at any given moment. Shadowed regions would be bitterly cold, perhaps -100 degrees Celsius or colder, while sunlit areas might warm to only slightly below freezing at their warmest moments. The contrast would be visible in infrared observations. The walls of Stickney have slumped in some locations, material sliding downward under the weak gravity of Phobos toward the crater floor below, over the long ages since the impact first carved this depression. This slumping has widened the crater slightly from its original dimensions and created debris aprons at the base of the walls, where material has accumulated after sliding down from higher elevations above. Even in weak gravity, material eventually moves downhill. The examination of Stickney could continue indefinitely, each new observation revealing additional details about this remarkable feature and the event that created it so long ago in solar system history. But other features of Phobos await attention, mysteries that may or may not be connected to this great impact, but certainly deserve exploration in their own right as significant characteristics of this strange, small moon orbiting Mars. The grooves that cross the surface beyond Stickney's rim pose questions that scientists are still working to answer. The grooves that cross portions of Phobos' surface represent one of the most puzzling features found on any moon in our solar system. Patterns that seem too organized to be random, yet resist easy explanation through any single theory. These linear trenches stretch for many kilometers across the terrain, running in roughly parallel sets that create a visual impression of scratches or furrows carved into the ancient surface by some unknown process operating long ago. The grooves appear to have stories to tell, but the language they speak remains only partially translated. The dimensions of these features are substantial enough to be visible from orbit. Trenches, typically 100 to 200 meters wide and perhaps 10 to 20 meters deep, carved into the regolith and underlying material. Some grooves extend for 30 kilometers or more, crossing significant fractions of the moon's small circumference before they fade or are interrupted by other surface features. The longest grooves could take hours to walk along, if walking were possible, on this airless, low-gravity world where human feet have never stepped. The parallel arrangement of the grooves within any given set suggests that they formed through a single process, operating consistently across the region, creating multiple trenches simultaneously or in quick succession by the same mechanism. Some sets of grooves appear to radiate outward from the region of Stickney crater, raising the possibility that the great impact we just explored might have created these features as shockwaves propagated through the small body of the moon. The alignment with Stickney is suggestive, but not conclusive. Other groove sets do not align with Stickney at all, their orientations inconsistent with the idea that they all formed as a consequence of that single enormous impact in the distant past. These non-aligned grooves demand alternative explanations, additional mechanisms that might have operated independently of the Stickney impact, or perhaps at different times in the moon's long history of bombardment and geological evolution. The grooves are not all the same. The Stickney impact theory proposes that the grooves formed when the enormous collision sent shockwaves propagating through Phobos' small body, fracturing the surface in patterns that reflected the internal structure and the geometry of the impact event itself. The moon would have rung like a bell from the impact, vibrations traveling through its interior and creating stress patterns that cracked the surface along lines determined by the physics of wave propagation through solid material. This explanation accounts for many groove features. An alternative theory suggests that the grooves trace the paths of debris ejected from Mars itself during ancient impacts on the planet. Material that struck Phobos in sequential chains as the Moon moved through streams of orbiting debris. This mechanism would create parallel trenches as lines of material struck the surface along Phobos's orbital path. Each impact too small to create a distinct crater, but collectively carving shallow grooves through repeated strikes. The idea has appeal, but difficulties. More recent research has proposed that the grooves might be stretch marks, cracks forming in the surface as Phobos is gradually pulled apart by the tidal forces exerted by Mars as the Moon spirals slowly inward toward the planet that holds it in orbit. This theory connects the grooves to the ongoing death of Phobos, the slow doom that will eventually either drop this Moon onto Mars or tear it into fragments that form a ring around the red planet. The grooves become evidence of destruction in progress. The tidal stress theory gains support from observations of groove orientations that align with the direction of tidal forces, rather than with Stickney or any other impact feature on the surface. If Phobos is being stretched along the axis pointing toward Mars, cracks would form perpendicular to that stretching direction. And some groove sets do appear to follow this predicted orientation reasonably well. The Moon may be cracking like an eggshell under slow pressure. No single theory explains all the grooves on Phobos, and the reality may involve multiple processes operating at different times across the Moon's long history orbiting Mars. The Stickney impact may have created some grooves, while tidal stresses are creating others, now or in the geologically recent past. Rolling boulders may have carved still others, as large rocks ejected from craters bounced across the surface before coming to rest. The grooves record multiple chapters. Walking along one of these grooves would be a strange experience, the walls rising gently on either side, as the trench stretches ahead toward the too close horizon of this small world. The floor would be covered in the same regolith that blankets everything. Fine dust accumulated since the groove formed whenever that might have been in the past. The parallel groove beside this one would be visible as a similar shadow crossing the terrain, the pattern repeating across the landscape in its puzzling regularity. The depth of the grooves is shallow relative to their width, creating features that would feel more like wide valleys than narrow canyons to any observer standing within their boundaries. The aspect ratio differs from typical river valleys or fault lines on Earth, suggesting that whatever process formed these features operated differently than familiar terrestrial geology. The grooves are uniquely Phobian. Scientific investigation of the grooves continues as new data arrives from spacecraft that visit the Mars system and examine Phobos from various distances and angles over time. The Mars Express spacecraft has provided detailed images that reveal groove characteristics invisible to earlier missions, and future dedicated missions to Phobos may finally resolve the questions that these features raise about the Moon's history. Understanding requires patience. The grooves connect Phobos to larger questions about how small bodies respond to impacts and tidal stresses and other forces operating in the solar system environment across astronomical timescales. What we learn here applies to asteroids, to other small moons, to objects throughout the solar system that experience similar processes without human observers nearby to document the results. Phobos serves as a laboratory, The mystery of the grooves enhances the strangeness of Phobos, adding intellectual texture to a world that already defies easy categorization through its irregular shape, dark surface, close orbit, and dramatic impact scarring visible across much of its visible hemisphere. This is not a simple world, but rather a complex one, full of features that invite explanation and resist complete understanding despite decades of study by planetary scientists on Earth. The questions continue. Beyond the dramatic features of craters and grooves, the actual experience of being on Phobos would involve confronting the strange surface conditions that exist nowhere else quite like this place. Gravity so weak, it barely holds you down, a landscape covered in ancient dust, and the overwhelming presence of Mars filling the sky above. The surface itself awaits exploration. The surface of Phobos presents an environment unlike any place on Earth, a landscape where the familiar rules of movement and perception would need to be entirely relearned by any visitor fortunate enough to stand there someday. The most immediately strange aspect would be the gravity, so weak on this small moon that it barely deserves the name at all. Phobos possesses only about 1/1000th of Earth's surface gravity, meaning a person who weighs 80 kilograms on Earth would weigh less than 100 grams here on this dark, ancient world. The implications of this extraordinarily weak gravity become apparent when considering any normal physical activity that depends on weight for traction or stability in familiar environments. Walking would be nearly impossible in any conventional sense, each step pushing you upward rather than forward, the ground offering almost no resistance to push against effectively. Movement would require something closer to swimming or climbing, using handholds or tethers rather than relying on friction between feet and ground. That simply does not exist in meaningful amounts here. Throwing a rock on Phobos would produce results that violate every intuition developed through a lifetime of living under Earth's gravity in our familiar environment. A moderate throw could send a rock traveling for many minutes before it finally returned to the surface, arcing slowly across the sky in a trajectory that would seem impossibly stretched to Earth-trained eyes watching the path unfold. A harder throw, perhaps 25 miles per hour, could achieve escape velocity entirely, sending the rock into orbit around Mars rather than back to the surface of the moon you threw it from. The escape velocity from Phobos is only about 11 meters per second, roughly the speed of a fast human sprint or a moderate bicycle ride on Earth roads. This means that a sufficiently energetic jump could theoretically launch a person completely off the moon, no rocket required, though the jump would need to be carefully controlled to avoid tumbling or misaligning the trajectory from the surface. The low gravity creates both opportunities and challenges. The surface underfoot would be covered in regolith, the layer of broken and pulverized rock that blankets every solid body in the solar system, exposed to the bombardment of space over billions of years of cosmic history. This material forms through impacts of all sizes, each collision grinding surface rock into finer particles that accumulate gradually over time into a blanket covering the underlying bedrock completely in most locations. The regolith on Phobos may extend 100 meters deep in some areas. The texture of this regolith would be fine, but not uniform, particles ranging from microscopic dust to pebbles to larger fragments embedded in the matrix of finer material coating everything. The color is dark gray to slightly reddish brown, absorbing most of the light that strikes it, rather than reflecting it back toward any observer looking at the surface. Your footprints would sink slightly into this material, perhaps a centimeter or two, leaving marks that would remain unchanged for millions of years in this airless environment. Boulders interrupt the regolith blanket here and there, rocks too large to be fully buried by the finer material that surrounds them on the ancient surface. The largest of these boulders reaches perhaps 85 meters across, a substantial mass of rock sitting on the surface like a monument to some ancient impact that ejected it from elsewhere on the moon. These boulders would provide landmarks for navigation across a surface where the close horizon makes distant features difficult to see. The temperature at the surface would vary dramatically depending on whether you stood in sunlight or shadow at any given moment during the exploration. Sunlit areas might warm to only slightly below freezing, perhaps -4 degrees Celsius under favorable conditions during Phobos's closest approach to the sun. Shadowed areas plunge to temperatures around -112 degrees Celsius, or even colder in deep shadows that never receive direct sunlight. The transition between these temperature extremes would be sharp, the boundary between sunlight and shadow crossing the surface as a distinct line rather than a gradual gradient. Without any atmosphere to scatter light or transfer heat through convection, the sunlit side and the shadowed side exist in completely separate thermal conditions, despite being mere meters apart on the same small world. Stepping from light into shadow means stepping into a different thermal universe. The horizon appears remarkably close on Phobos, the small size of the moon, creating a surface that curves away noticeably in every direction from any observer standing at ground level. The farthest visible point might be only 2 or 3 kilometers distant, compared to about 5 kilometers on Earth at sea level under clear conditions. This close horizon creates a sense of intimacy with the landscape. Mars dominates the sky above, the red planet appearing enormous from Phobos's surface because of the extraordinarily close orbit that keeps this moon nearer to its planet than any other moon in the solar system. The planet spans about 8 degrees of arc, as seen from Phobos. Roughly 16 times wider than Earth's moon appears from our home world's surface. Surface features are visible without magnification. The appearance of Mars would change dramatically over the course of each orbit, as Phobos races around the planet. Different regions rotating into view as the geometry shifts between moon and planet during the rapid orbital period. Dust storms would be visible as darker smudges crossing the rusty surface, polar caps gleaming white at the planet's extremes, and the great volcanoes of the Tharsis region perhaps catching sunlight on their enormous slopes. Mars is not just present, but overwhelming. Stars would be visible in the black sky even during periods when the sun illuminates the surface, no atmosphere existing to scatter light and create the blue sky that hides stars during Earth's daytime hours. The stars would appear fixed and steady, none of the twinkling caused by atmospheric turbulence on our home world. Pure points of light against pure blackness stretching in every direction, not occupied by Mars or the Sun. The universe feels very close. The Sun itself appears smaller from this distance, further from the center of the solar system, where light is weaker and the disk of the Sun spans fewer degrees of arc in the sky above. The illumination is noticeably dimmer than on Earth, perhaps 1/2 to 1/3 as bright, depending on the distance from the Sun during Mars's elliptical orbit around it. The light is enough to see by, but creates a different quality of illumination. The silence would be absolute. No atmosphere existing to transmit sound waves between sources and listeners on this airless world circling Mars. A hammer strike against rock would produce vibrations you might feel through contact, but no sound traveling through air to reach your ears. The only sounds would come from inside whatever suit or habitat contained you. The quiet would be complete. Phobos provides an environment for exploration unlike any other place humans might someday visit. Strange enough to challenge every expectation while remaining technically within reach of human spacecraft using technology that already exists or could be developed. The experience would be transformative for anyone fortunate enough to stand on this dark, ancient surface beneath the enormous presence of Mars filling the sky above. But other aspects of Phobos deserve attention before we move on. The orbit that carries Phobos around Mars is among the most remarkable of any moon in the solar system. Closer to its parent planet than any other moon, and racing through each orbital circuit at speeds that create phenomena seen nowhere else in our planetary neighborhood. The orbital distance averages only about 9,376 kilometers from the center of Mars, which places the surface of Phobos only about 6,000 kilometers above the Martian surface itself at closest approach. This proximity defies comparison. The closeness of Phobos to Mars means that the moon completes its orbit in just 7 hours, 39 minutes, and 12 seconds, racing around the planet, while Mars rotates much more slowly beneath it through the Martian day. Mars takes about 24 hours and 37 minutes to complete one rotation, meaning that Phobos circles the planet more than 3 times during a single Martian day of rotation. The moon is faster than the planet. This difference in speeds creates a phenomenon unique to Phobos among all the moons of the solar system. The moon rises in the west and sets in the east, exactly opposite the direction of every other celestial body, crossing the sky from the perspective of a Martian surface observer. The sun rises in the east and sets in the west on Mars, just as on Earth. But Phobos moves the wrong way, tracking backward against the stars, because it orbits faster than the planet rotates beneath its rapid orbital path. An observer standing on Mars, near the equator, would see Phobos appear above the western horizon, then track steadily eastward across the sky over a period of about 4.5 hours before setting below the eastern horizon and disappearing from view. The motion would be clearly visible against the background stars, the moon moving noticeably over periods of just a few minutes, rather than the slow creep that Earth's moon demonstrates across our own night sky. Phobos is in a hurry. The rapid orbital period means that Phobos rises and sets approximately 3 times during each Martian day, appearing in the western sky, crossing overhead, setting in the east, then coming around again to repeat the performance multiple times before the Martian night ends and the sun returns. The relationship between moon and planet feels dynamic, constantly changing, unlike the stately once-per-month cycle that Earth's moon traces across our familiar night sky. From Phobos itself, Mars would not rise or set at all from most locations on the moon's surface, because Phobos is tidally locked to Mars, always showing the same face toward the planet it orbits, just as Earth's moon always shows the same face toward Earth. From the side facing Mars, the planet would hang motionless in the sky, enormous and ever-present, rotating slowly as Phobos completes each rapid orbit, but never rising or setting from that vantage point. Mars would simply be there. The tidal locking means that Phobos has a near side and a far side relative to Mars, regions that either always face the planet or always face away into the darkness of space beyond. The near side receives constant illumination from light reflected off Mars, while the far side experiences only the much weaker light from the distant sun. The two hemispheres exist in different lighting environments, but the orbital dynamics that create these strange phenomena come with a consequence that makes Phobos unique in another way. This moon is slowly dying, spiraling inward toward Mars, with each passing century, as tidal forces drain energy from its orbit and convert it into heat within the moon's flexing interior. The doom is gradual, but inevitable. The orbital decay amounts to about 2 centimeters per year. A tiny distance that seems insignificant until you calculate the cumulative effect across millions of years of continued orbital shrinkage between moon and planet. Over 1 million years, the orbit shrinks by 20 kilometers. Over 50 million years, the process brings Phobos close enough to Mars that the gravitational stresses become overwhelming. The Roche limit represents the distance from a planet within which tidal forces exceed the internal gravitational forces, holding a moon together as a coherent body. For Phobos orbiting Mars, this limit lies approximately 7,000 kilometers from the center of Mars, closer than Phobos currently orbits, but not by a comfortable margin given the ongoing orbital decay. The limit is approaching. In approximately 50 million years, Phobos will cross the Roche limit and face one of 2 possible fates, depending on its internal structure and the precise details of the final approach to destruction. The moon might crash directly into Mars, creating an impact crater visible from Earth and depositing the material of Phobos across the Martian surface in a collision event. Or the moon might break apart first. The breakup scenario seems more likely based on current understanding of the forces involved and the probable internal structure of this small, irregularly shaped body that may already be developing cracks, visible as the grooves we explored earlier in our journey tonight. As Phobos crosses below the Roche limit, tidal forces would stretch the moon beyond its structural limits, pulling it apart into fragments that would initially remain along the same orbital path. These fragments would gradually spread along the orbit, colliding with each other and breaking into smaller pieces, eventually forming a ring around Mars, similar to the rings around Saturn, but composed of much darker material derived from the destroyed moon. Mars would briefly possess a ring system, a feature it has never had during the period humans have observed it, but one that may have existed in the past and may exist again. The ring would not last forever, the fragments continuing to spiral inward, just as Phobos itself is spiraling inward now, eventually raining down onto the Martian surface as a prolonged meteor shower, lasting perhaps millions of years after the initial breakup of the moon. Mars would accumulate a thin layer of Phobos material across its surface. The grooves on Phobos may represent the early stages of this destruction. Cracks forming as tidal stresses already begin to pull the moon apart slowly, stretching it along the axis, pointing toward Mars, with forces that will eventually overcome the structural integrity, holding the moon together as a single body. If this interpretation is correct, we are watching a moon in the process of dying, its surface recording the forces that will eventually destroy it. The death of Phobos is certain on geological timescales, written in the physics of orbital mechanics that cannot be argued with or avoided through any natural process. But 50 million years is a long time by human standards. Long enough for whatever future exists for humanity, and long enough for many more missions to study this doomed moon before its inevitable end arrives in the distant future. For now, Phobos continues. Having explored the larger moon thoroughly, we return now to its smaller sibling orbiting farther from Mars in a more stable configuration. Deimos, with its softened surface and patient orbit, waiting to reveal its own character through closer examination of the features that make it distinct from Phobos, despite their probable shared origins in the ancient solar system. Standing on the surface of Deimos would present an experience even stranger than standing on Phobos. The gravity here so weak as to make normal movement nearly impossible by any standard familiar to bodies that evolved on Earth. The surface gravity on Deimos is approximately 3/1000ths of Earth's gravity, meaning a person who weighs 80 kilograms on Earth would weigh only about 240 grams on this tiny world orbiting far from Mars. This is lighter than a large apple, lighter than a cup of coffee, lighter than almost any object you might pick up casually during a normal day back home. The implications for movement are profound and would transform every familiar action into something requiring entirely new approaches learned from scratch. Walking would not work here in any conventional sense that we understand, from a lifetime of experience, moving across Earth's surface with meaningful friction beneath our feet. The push of each step would send you drifting upward rather than propelling you forward along the ground. The weak gravity unable to return you quickly to the surface for the next step in a walking sequence. No amount of practice would restore the physics that makes walking possible on worlds with meaningful gravity holding everything down against the solid ground below our moving feet. Movement on Deimos would require handholds, tethers, or some form of propulsion system that does not depend on friction with the ground for traction in any way at all. Astronauts would essentially float across the surface, touching down occasionally and pushing off again. More like swimming through the environment than walking across it in any conventional understanding of locomotion. The body would need to learn entirely new reflexes suited to an environment where up and down barely exist in the gravitational sense that shapes all movement on Earth constantly. Every motion would need to be gentle and controlled. Any sudden movement risking an unintended launch that might carry the careless explorer far from their intended path across the dark terrain. The learning curve would be steep, but the reward would be experiencing a world unlike any other place humans have ever stood or may ever stand. The escape velocity from Deimos is only about 5.6 meters per second, roughly the speed of a fast jog or a moderate bicycle ride along a flat road on Earth without significant effort. This means that a person who jumped with sufficient vigor could potentially launch themselves completely off the moon. No rocket required, achieving escape through muscular effort alone. The weak gravity offers both freedom and danger. The possibility of exploring with almost supernatural ease, balanced against the risk of accidentally leaving the moon entirely through an overly enthusiastic jump. Any activity on the surface would need to proceed with careful attention to velocity. Every movement measured against the threshold that separates exploration from unintended orbit. The regolith underfoot would feel soft beneath any boot or instrument that touched it. The thick layer of pulverized material yielding slightly to any pressure applied from above. Footprints would sink gently into the accumulated dust of billions of years before slowly settling back toward their original configuration in the near absence of gravity, pressing things down firmly. The material is dark grey to slightly reddish brown, absorbing most light that strikes it and giving the surface a matte quality that seems almost soft in appearance. Every step would disturb this ancient material, sending particles drifting slowly outward in trajectories that would take many seconds to complete before settling back to the surface below. The horizon on Deimos lies remarkably close, perhaps only 2.5 kilometers distant from any observer standing at ground level. On this small world that curves away visibly in every direction, the curvature of the surface is obvious to the eye, the ground falling away noticeably as if standing on a very small hill that somehow extends endlessly in all directions simultaneously. The entire moon feels graspable and comprehensible, finite in a way that larger worlds never allow observers to perceive directly through simple visual inspection of the surrounding terrain. You could see the curve of this world simply by looking toward any horizon. The smallness of Deimos impossible to ignore or forget for even a moment of observation. From this surface, Mars appears smaller in the sky than it does from the surface of Phobos, the greater orbital distance, reducing the planet's apparent size to something more manageable but still impressive by any Earth standard. The planet spans roughly 4 degrees of arc from Deimos, about 8 times the width of Earth's moon, as seen from our homeworld's surface below familiar night skies. The red disk of Mars would show clearly visible surface features even without magnification, dust storms appearing as darker smudges crossing the rusty terrain, while polar caps gleam white at the planet's extremes. The great volcanoes might be visible as slight bulges interrupting the smooth limb of the planet against the black sky beyond, where the stars wait in their fixed positions. Mars is present from Deimos, but not overwhelming, a companion rather than a dominating presence that fills the sky and commands attention away from everything else visible above. The relationship feels more distant here, less immediate, as befits a moon that orbits nearly 4 times farther from its planet than Phobos does in its close and hurried path. The greater distance creates space for other observations, other thoughts, other relationships with the cosmos beyond the Mars system that holds both small moons in its gravitational embrace. Looking up from Deimos, you would see Mars clearly, but you would also see the universe stretching beyond it in every direction, toward infinity. The Sun appears smaller from this distance in the outer reaches of the inner solar system, farther from the center than Earth orbits, providing less illumination, but still enough light to see clearly across the dark surface during sunlit periods. The quality of light feels different from what we know on Earth, somewhat dimmer and perhaps subtly different in color temperature as the greater distance changes the relationship between observer and star. Shadows would be sharp and dark in this airless environment where no scattered light fills the spaces that direct sunlight cannot reach between surface features. The contrast between lit and unlit regions would be extreme. Stars fill the sky in every direction not occupied by Mars or the Sun. Steady points of light without the twinkling caused by atmospheric turbulence on Earth, because no atmosphere exists here to disturb incoming photons. The universe feels close from this vantage point. the barrier between the small moon's surface and the greater cosmos reduced to almost nothing by the absence of any intervening medium. You could look directly at star fields that would be invisible from Earth's surface during daytime hours, the black sky revealing its treasures, regardless of whether the sun currently illuminates the ground beneath your feet. The celestial sphere surrounds you completely here. The temperature would vary dramatically between sunlit and shadowed regions. Just as on Phobos, the lack of atmosphere, creating sharp thermal boundaries where light meets darkness across the surface terrain. Sunlit areas might warm to near freezing temperatures, while shadowed zones plunge to -100 degrees Celsius or colder, depending on how long they have remained in darkness. The contrast would be visible in any thermal imaging, and the experience of moving from sun to shadow would mean moving between entirely different thermal environments in the space of a single step. The suit that protects any visitor would need to manage these transitions constantly. The silence on Deimos would be absolute. No sound traveling through the vacuum between sources and listeners. Every vibration confined to solid materials that conduct it through direct contact only. The footsteps that would be so strange and difficult would also be completely silent to any ear not in direct contact with the surface material, transmitting vibrations from the impact. Your own breathing would be the loudest thing in this world. The sounds of your body, the only audio accompanying the visual spectacle unfolding around you in every direction. The quiet would be profound in ways that Earth can never offer. Mars hangs steady in the sky from most vantage points on Deimos because the moon is tidally locked, always showing the same face toward the planet it orbits slowly through each 30-hour circuit. The planet does not rise or set from locations on the Mars-facing hemisphere, but simply hangs motionless in the black sky, rotating slowly as hours pass, but otherwise fixed in position perpetually. From the far side of Deimos, Mars would never be visible at all, the small moon's body blocking the view of the planet it orbits from those locations entirely. The two hemispheres experience very different skies. The patience of Deimos becomes apparent through extended observation, the slow rotation of Mars visible across the many hours required to notice any significant change in surface features facing the observer. The stars wheel overhead as the moon completes its leisurely orbit, compared to the hurried racing of Phobos around the inner reaches of the Mars system close to the planet. Time moves differently here, the pace of celestial motion slower and more contemplative than the frantic activity visible from the inner moon, where everything happens faster. Deimos invites patience rather than demanding the urgent attention that Phobos commands through its rapid orbital period. The surface tells its own quiet story through the softened craters and thick regolith blanket that covers everything. Evidence of billions of years of gentle accumulation rather than dramatic events. Deimos seems to have had a calmer history than its larger sibling, the violence of ancient impacts muted by time and dust into something approaching peace across the long ages. The craters are present but rounded, the features are visible but soft. The overall impression is of a world that has settled into quiet endurance rather than active transformation. This is a patient moon. The two moons together present contrasting characters orbiting the same planet in the same system, yet experiencing very different conditions and facing very different fates. One is scarred and hurried and doomed, while the other is smoothed and patient and stable in its distant orbit around Mars. Their shared origin leading to divergent destinies. The comparison invites reflection on how initial conditions and orbital dynamics shape the long-term evolution of small bodies throughout the solar system and beyond. Both emerged from similar beginnings but will end very differently. The surface of Deimos has now received thorough exploration through our attention. The soft regolith and gentle craters and weak gravity and patient orbital motion, all contributing to a portrait of a world quite different from its larger sibling. The experience of being here would be profound in its strangeness, the familiar rules of movement and perception requiring complete revision for this environment, unlike anywhere else humans have ever been. We leave the surface now to consider the orbital dynamics that give Deimos its stability and long future, the physics that separates its fate so completely from the doom awaiting Phobos in the geologically near future ahead. The orbit of Deimos presents a striking contrast to the doomed path that Phobos follows around Mars, distance from the planet creating stability, where proximity creates inevitable decay and eventual destruction for the inner moon. Deimos orbits at approximately 23,500 kilometers from the center of Mars, nearly 4 times farther out than Phobos, at its much closer distance of only about 9,400 kilometers. This greater distance translates into a much longer orbital period, Deimos taking 30 hours and 18 minutes to complete each circuit around Mars, compared to the rushed 7 hours and 39 minutes Phobos requires. The difference in orbital speed shapes everything about how these two moons experience their relationship with the planet. They both circle endlessly. The length of the orbital period means that Deimos rises in the east and sets in the west, following the expected direction for celestial objects crossing the sky, rather than the backward motion that characterizes Phobos. From the Martian surface, Deimos behaves like a normal celestial object, moving in the same direction as the stars and sun across the sky during each Martian day. This conventional motion occurs because Deimos orbits more slowly than Mars rotates beneath it. The opposite situation from Phobos, which races around faster than the planet can keep up. The two moons move in opposite directions across the Martian sky, despite orbiting in the same direction around the planet itself. The slowness of the orbital motion means that Deimos takes approximately 60 hours to cross the Martian sky from horizon to horizon, creeping gradually against the background stars. This pace is so gradual that short-term observers might not notice any motion at all without careful tracking of the moon's position relative to fixed reference points over extended periods. An observer on Mars watching Deimos would need patience to perceive its motion. The small moon hanging in roughly the same position night after night, with only subtle changes. Compared to Phobos racing across the sky and rising again within hours, Deimos seems almost stationary in its unhurried journey across the darkness above. The size of Deimos in the Martian sky is much smaller than Phobos appears. The combination of smaller physical dimensions and greater orbital distance reducing this outer moon to something roughly star-like. Deimos would appear as a very bright point of light, rather than the disk-like object that Phobos presents to naked eye observers standing on the Martian surface below. The brightness would be notable, perhaps comparable to Venus as seen from Earth. But the small angular size would prevent any observer from resolving surface details without optical assistance. The two moons look very different from the planet they both orbit. Transits of Deimos across the Sun are less noticeable than transits by Phobos, because the smaller apparent size makes the outer moon appear as merely a dark point rather than a significant obstruction. The transit would be scientifically interesting, but visually subtle compared to similar events involving the larger inner moon crossing the solar disk in its rapid passage. Scientists have observed these transits using cameras on Mars rovers, but the events lack the drama of Phobos transits that show an obvious irregular shape against the burning disk. Deimos simply dots the sun briefly during its slow passage. The tidal locking that affects both moons means Deimos always shows the same face toward Mars, just as Phobos does, and just as Earth's moon always shows the same face toward our home planet. From Deimos, Mars would hang motionless in the sky from locations on the Mars-facing hemisphere, rotating slowly but never rising or setting through the local horizon. The far side of Deimos never sees Mars at all, the small moon's body perpetually blocking the view of the planet from those locations on the surface permanently. This creates two very different experiences depending on where you stand on the small moon's surface. The key difference in orbital dynamics concerns the long-term fate of each moon, the physics of tidal interactions determining whether an orbit will expand or contract over time, based on specific relationships. Phobos orbits faster than Mars rotates, completing more than 3 orbits during each Martian day, and this configuration causes tidal interactions to drain energy from the orbit continuously. The energy loss causes the moon to spiral slowly inward toward eventual destruction when it crosses the Roche limit or crashes into the Martian surface directly. The physics is inexorable, and the outcome is certain for the inner moon. Deimos orbits slower than Mars rotates, taking longer to complete each orbit than Mars takes to rotate once beneath the orbiting moon during each Martian day cycle. This configuration causes tidal interactions to add energy to the orbit, rather than draining it away, causing the moon to spiral slowly outward away from the planet over very long timescales. The physics operates in reverse, compared to Phobos, building orbital energy rather than depleting it, expanding the orbit rather than shrinking it toward destruction. The difference in orbital period relative to planetary rotation determines everything. The outward spiral of Deimos is extremely slow, much slower than the inward spiral of Phobos, because the tidal forces are weaker at greater distances from the planet. The expansion may amount to only fractions of a centimeter per year, a rate so gradual that millions of years would be required to produce changes measurable by current instruments observing from Earth. Over billions of years, however, this slow expansion will carry Deimos farther and farther from Mars, weakening the gravitational bond between moon and planet incrementally. The process has plenty of time to operate. Eventually, perhaps billions of years from now, Deimos may escape from Mars entirely if the outward spiral continues long enough and carries the moon beyond the gravitational sphere of influence. The escape would not be dramatic, but rather a gradual transition as the moon drifts outward until the sun's gravitational influence exceeds that of Mars on the small body's trajectory. Alternatively, Deimos may remain bound to Mars indefinitely, the expansion slowing or stopping at some equilibrium distance, where tidal forces no longer cause significant orbital changes over any reasonable timescale. The final outcome depends on details that current models cannot predict with certainty. What is certain is that Deimos faces a very different fate than Phobos, one measured in billions of years rather than tens of millions, one leading away from Mars rather than toward it. This future may preserve the small moon long after its larger sibling has been destroyed and scattered across the Martian surface, or into a temporary ring encircling the planet. The contrast could not be more complete between two moons orbiting the same planet in the same general region of the solar system today. Their fates diverge as completely as orbital mechanics allows. The contrast between the two moons' destinies raises questions about their origins, whether they formed together or separately, whether they arrived at Mars through similar or different processes long ago. Both share characteristics that suggest possible common origins, despite their different current circumstances and dramatically divergent futures awaiting them ahead. The dark coloring, the irregular shapes, the probable composition all point toward related histories, even if the specific details remain uncertain, pending future investigation. Understanding where they came from helps explain where they are going. The orbital dynamics of Deimos provide a kind of security that Phobos will never know. The physics of its situation ensuring continued existence through timescales comparable to the remaining lifetime of the Sun itself. This stability makes Deimos a different kind of object for scientific study, a moon that will remain available for observation and exploration indefinitely, rather than one racing toward destruction in the geologically near future. The urgency that might apply to studying Phobos before it disappears does not apply to Deimos in the same way at all. There is time. The relationship between Mars and its outer moon will continue largely unchanged for eons to come. The planet and moon circling together around the Sun, while the distance between them gradually increases at rates too slow to notice across human timescales. Future generations will see essentially the same Deimos that we see today, the same slow motion across the Martian sky, the same patient orbit, the same gentle surface covered in ancient regolith accumulated across billions of years. Deimos endures. The stability of Deimos contrasts not only with the doom of Phobos, but also with the violence that may have created both moons in the distant past, through processes we are only beginning to understand. The origins of these strange small moons remain uncertain. Multiple theories competing to explain how they came to orbit Mars in their current configurations around the red planet. The question of where they came from deserves exploration as we continue our journey through the Mars system tonight. The question of where Mars's two small moons originally came from has puzzled planetary scientists since Asaph Hall first spotted them through his telescope at the Naval Observatory in Washington. During August of 1877, the answer remains uncertain after nearly 150 years of study, multiple theories competing to explain how these dark, irregular bodies ended up orbiting the red planet in their current configurations. Each theory has strengths and weaknesses, evidence that supports it, and observations that challenge its completeness as an explanation for what we actually see today. The mystery continues to drive scientific investigation. The dominant theory for many years suggested that Phobos and Deimos are captured asteroids, small rocky bodies that originally formed elsewhere in the solar system and were somehow deflected into paths that brought them close enough to Mars for gravitational capture. The dark colors and low reflectivity of both moons support this idea. matching the characteristics of certain asteroid types found in the outer regions of the asteroid belt beyond Mars. The spectral signatures observed from both moons resemble D-type or C-type asteroids, carbonaceous objects whose compositions have remained largely unchanged since the early solar system formed from the original nebula. The match between moon spectra and asteroid spectra is close enough to seem significant. If the moons are captured asteroids, they would represent material from the outer solar system that somehow migrated inward toward Mars and approached at just the right velocity and angle. The capture would have required special circumstances because simple gravitational encounters typically deflect passing objects rather than trapping them in stable orbits around a planet. Something would have needed to remove enough energy from the approaching asteroids to slow them below escape velocity during their close passages by Mars. The mechanics are challenging, but not impossible. The problem with the capture theory is that capturing an asteroid into a stable orbit is dynamically difficult, requiring circumstances that seem unlikely to have occurred by chance alone, without some additional mechanism assisting. An asteroid approaching Mars at typical solar system velocities would swing past the planet on a hyperbolic trajectory, gaining some gravitational deflection but retaining enough energy to escape, rather than being trapped. Simple gravitational capture does not work for objects approaching at normal interplanetary velocities, without additional energy dissipation mechanisms operating simultaneously. Something else must slow the asteroid down. One proposed mechanism involves Mars having a much more extended atmosphere early in its history, a thick envelope of gas that might have provided enough aerodynamic drag to slow approaching asteroids. This atmospheric braking could have removed sufficient energy during close passages through the upper atmosphere to leave the asteroids trapped in bound orbits around Mars permanently. The atmosphere would have been temporary, present only during the early history of Mars, before being lost to space through various processes, operating over billions of years afterward. The timing would need to match the arrival of the asteroids. Another possibility involves close encounters during which approaching asteroids were actually disrupted by tidal forces or collisions with existing debris orbiting Mars during the early solar system period. Some fragments from such disruption events might have achieved lower velocities, allowing capture, while other fragments escaped back into independent orbits around the Sun. The process would have been messy and probabilistic, depending on specific encounter geometries that could have gone many different ways, with different outcomes in each case. Some small fraction of encounter scenarios might have produced captures. The alternative to capture suggests that Phobos and Deimos formed in place, created from debris thrown into orbit around Mars during one or more giant impacts early in the planet's history. Large objects striking Mars would have ejected enormous quantities of material into space, some of which could have achieved velocities sufficient to reach orbit rather than falling back to the surface immediately. This ejected material would have formed a disk around Mars from which the moons could have coalesced through the same accretion processes that built larger bodies throughout the early solar system. The formation theory has gained support in recent years. The giant impact theory explains some features of the moons that capture theory struggles with, particularly the nearly circular and nearly equatorial orbits that both moons currently occupy around Mars today. Captured asteroids would typically enter highly elliptical orbits, with random orientations determined by their approach trajectories rather than by any relationship to the planet's equator or rotation. The tidy orbital configuration actually observed suggests an origin more closely connected to Mars itself than random capture would produce naturally. The orbits look like formation rather than capture. Material ejected from Mars by a giant impact would naturally form a disk around the planet, concentrated in the equatorial plane, where most of the ejected material's angular momentum would place it. Moons forming from this disk would inherit the circular, equatorial characteristics that we actually observe in the orbits of Phobos and Deimos today, without requiring any special explanation or unlikely circumstances. The orbital geometry supports the formation hypothesis strongly against capture alternatives that struggle to explain the same observations convincingly. The geometry tells a story. The difficulty with the formation theory is explaining the dark, asteroid-like composition of both moons, which differs significantly from the composition of Mars itself, as we understand it from meteorite samples and remote observations. Material ejected from Mars should resemble Martian rock in its spectral properties, but the moons look more like outer belt asteroids than like pieces of Mars do when observed with the same instruments. This compositional mismatch challenges the simple formation theory and requires additional explanation to resolve the apparent contradiction between orbital geometry and surface chemistry observations. The contradiction is real. One resolution suggests that the impacting body itself was a carbonaceous asteroid, and the moons formed primarily from this impactor material, rather than from Martian crustal rock ejected by the collision. The moons would inherit the dark coloration of the original asteroid, while acquiring orbits determined by the impact geometry and disk formation processes operating after the collision event. This hybrid explanation combines elements of both capture and formation theories into something that might explain both the orbits and the composition simultaneously. The idea is elegant. The Japanese Space Agency has planned a mission called Martian Moons Exploration, designed to address these questions directly through sample collection and return to Earth for laboratory analysis. The mission will visit Phobos, land on its surface, collect samples of the regolith covering the moon, and return those samples to Earth using technology developed through decades of space exploration experience. The returned samples will be analyzed using instruments far more sophisticated than any that could be carried on a spacecraft to the distant Mars system for in-place measurements. The analysis may finally answer the origin question definitively. If the samples show primitive, carbonaceous composition matching outer belt asteroids, the capture theory gains support despite the dynamical difficulties that make capture seem unlikely without special circumstances helping. If the samples show processed material similar to Martian rock or impact mixed compositions containing both Martian and primitive asteroid components, the formation theory gains support, instead, as the better explanation. Either result would represent a major advance in understanding the origin and evolution of the Mars system and similar systems around other planets throughout the solar system. The samples will tell the story. The origin of these moons matters beyond Mars itself, because it helps us understand the processes that shaped the early solar system more broadly through gravitational interactions and impact events. Whether small bodies can be captured into stable orbits around planets, whether giant impacts can create moons through debris disk formation, and what the compositional signatures of these different processes might look like, are all questions with implications extending far beyond Mars. Learning the answer for Phobos and Deimos teaches us about moon formation everywhere. whether captured wanderers or children born from violence in orbit around Mars. Phobos and Deimos have circled the red planet for billions of years as patient companions through all the ages since their orbits were established. Their current reality matters as much as their uncertain origins. Their presence in the Martian sky creating phenomena that future human visitors will experience directly as they look up from the surface of the world they hope to explore. The moons wait for closer examination by human eyes. The view from the Martian surface reveals both moons as active participants in the planet's sky, moving across the darkness in patterns unlike anything visible from Earth or any other world where humans have lived or might someday make their homes. Future visitors to Mars will look up and see two moons where we are accustomed to. One, each moon following its own rules of motion and appearance, in ways that will seem strange at first. The Martian sky offers something genuinely new to observers who have only known Earth's familiar single companion, tracing its stately monthly path across our night sky. The novelty will be profound. Phobos appears as the more prominent of the two moons from the Martian surface, spanning roughly 1/3 the angular width of Earth's moon, as seen from our home world below familiar night skies. This size is large enough to show an irregular shape to careful naked eye observers who take time to look closely at the small moon crossing above them in its rapid journey. The potato-like form that we explored earlier would be apparent as an elongated shape rather than the circular disk we expect from moons based on our experience with Earth's large, round companion. The irregularity marks Phobos as something different. The motion of Phobos across the Martian sky is its most striking characteristic for any observer watching from the surface of the planet below, where it races through orbit after orbit. The moon rises in the west, when all other celestial objects rise in the east, tracking backward against the stars at a pace visible over periods of just a few minutes. The crossing takes about 4.5 hours from western horizon to eastern horizon, the moon setting in the east after its backward journey across the Martian sky. The motion looks wrong to Earth-trained eyes. After setting in the east, Phobos reappears again in the west just a few hours later to repeat the performance as its rapid orbit brings it around to the visible side of Mars again and again. 3 complete crossings occur during each Martian day, the moon rising and setting repeatedly, while the slower rotation of Mars beneath cannot keep pace with the racing moon above. No other major moon in the solar system behaves this way, rising in the wrong direction and crossing the sky multiple times per day in its hurried orbit close to the planet. Phobos is unique. Deimos presents a very different appearance and behavior from its position higher and farther in the Martian sky, where it moves with patience rather than hurry across the darkness above. The smaller moon appears as little more than a very bright star-like point, rather than the disk-like object that Phobos presents to observers who look carefully at its irregular shape. The brightness would be notable, comparable perhaps to the brightest planets in Earth's sky, but the small angular size would prevent resolution of any surface details without optical magnification to assist the eye. Deimos barely seems to move. The motion of Deimos across the sky is so slow that careful observation over extended periods is required to notice any change in position at all against the background stars. The moon creeps eastward, following the expected direction, unlike its hurried sibling, but taking approximately 60 hours to complete the journey from one horizon to the other. This means the moon would remain visible for more than 2 full Martian days before finally setting below the eastern horizon and disappearing from view until it rises again. The patience of Deimos contrasts completely with the impatience of Phobos. The contrast between the two moons creates a dynamic sky unlike anything visible from Earth or any other planet in our solar system, where multiple moons can be observed from a solid surface. One moon races backward, while the other barely moves forward, both visible simultaneously during portions of each night in the Martian sky above. The visual effect would be remarkable to any observer accustomed to the simpler sky that Earth provides with its single large companion. Mars offers complexity where Earth offers simplicity. Eclipses and transits occur when either moon passes between Mars and the Sun, blocking or partially blocking the solar disk as seen from specific locations on the planetary surface below. These events differ significantly from total solar eclipses on Earth, because neither Martian moon is large enough to fully cover the Sun from the planet's perspective, given their small sizes and orbital distances. The moon simply passes across the solar disk without completely obscuring it, creating a transit rather than a true eclipse that would darken the sky dramatically. The Sun remains visible throughout. Phobos transits are the more visually dramatic events of this type, the larger moon appearing as a noticeable dark irregular shape crossing the solar disk over a period of only about 30 seconds. The rapid orbital motion carries the moon through the line of sight between observer and Sun quickly, the potato-shaped silhouette clearly visible against the bright disk behind it during the brief passage. The transit ends almost as soon as it begins, the moon continuing its hurried journey across the sky toward the eastern horizon ahead. Cameras on Mars rovers have captured these events. The rover's Curiosity and Opportunity have photographed Phobos transits from the Martian surface, capturing remarkable images of the irregular moon silhouetted against the Sun in observations that have been shared widely. These images confirm what calculations predicted about transit frequency and appearance, adding visual documentation to theoretical understanding of the phenomena that occur regularly in the Martian sky above. Scientists use these observations to refine orbital parameters and study the moon's positions with precision greater than other methods can achieve from Earth. The transits have practical value. Deimos transits are more subtle affairs compared to the dramatic silhouette that Phobos presents during its rapid crossings of the solar disk in the Martian sky. The smaller moon appears as merely a small dark point crossing the Sun, barely noticeable compared to the obvious irregular shape of its larger sibling during similar events. The transit takes longer because of the slower orbital motion, but the visual impact is much less striking to observers who might not notice the small dot crossing the bright disk at all. Deimos transits require more attention to observe. Neither moon creates anything resembling a total solar eclipse, because both are too small and too distant to fully cover the angular diameter of the Sun as seen from Mars. The illumination from the Sun continues essentially unchanged during transits. No dramatic darkening of the sky occurring as happens during total eclipses visible from Earth, when our larger moon covers the Sun completely for brief periods. Mars experiences partial shadowing at most during these events. The illumination provided by each moon during Martian nights differs substantially. Phobos bright enough to cast noticeable shadows when full, and overhead, while Deimos provides only stellar-level illumination, adding little to the darkness. Phobos, at its brightest, might provide roughly 1/40th the illumination of Earth's full moon, enough to see by, but not enough to read by or distinguish colors clearly. Deimos contributes even less light to Martian nights. The phases of Phobos cycle rapidly through the complete sequence from new to full and back again, the moon's orbital period of less than 8 hours, carrying it through all phase angles in well under a day. An observer watching through the night would see the phase change noticeably over the course of a few hours as the geometry between sun, moon, and observer shifts with the rapid orbital motion. The phases of Deimos change more slowly, but the moon is too small to show the phase variation clearly to naked eye observers anyway. Only Phobos displays obvious phases. Occasionally, the two moons interact visibly in the Martian sky. Phobos, passing in front of Deimos, as seen from certain locations on the planetary surface, below during alignments that occur irregularly. These mutual events add another layer of complexity to the dynamic sky that Mars provides to observers watching the dance of its two small companions across the darkness above. The events are predictable but not frequent. Special occasions when the geometry of both orbits places the moons along the same line of sight from specific observing locations. The moons occasionally meet. The human future on Mars will include these moons as constant companions in the sky above. Whatever settlements and outposts eventually dot the Martian surface across the coming decades of exploration and possible colonization, future residents will grow accustomed to seeing Phobos race across the sky multiple times per day, while Deimos hangs nearly motionless higher above in its slow journey from horizon to horizon. The moons will become familiar landmarks in an alien sky, their motions eventually seeming as natural to Martian colonists as the phases of our single moon seem to us today. Familiarity changes everything. Children born on Mars would grow up knowing two moons as their natural condition. The complex dance of Phobos and Deimos in opposite directions across the sky, seeming perfectly normal to minds that have never known anything else. They would find Earth's single moon strange in its lonely journey across a sky that seems empty by comparison to the dynamic complexity they call home above. The reversal of perspective would be complete for those whose only experience of moons comes from Mars rather than Earth's simpler arrangement with one large companion. Normal is what you know. Scientists working on Mars will have opportunities to study both moons far more closely than any observations from Earth can achieve. The proximity, allowing detailed investigation using relatively simple instruments and direct human observation. Questions that remain unanswered from Earth-based observation and robotic missions might find resolution through the more intensive study possible when human researchers live and work in the same planetary system as the objects they wish to understand. The presence of humans changes what becomes possible scientifically. The moons themselves might become destinations for human visitors at some point, targets for expeditions that could explore their surfaces directly and answer remaining questions about their composition, structure, and history through first-hand investigation. Phobos, in particular, has been proposed as a staging point for Mars missions, a place where spacecraft could rendezvous and resupply before descending to the Martian surface or returning to Earth. The low gravity would make landing and departing relatively simple, compared to the energy required for operations on the Martian surface itself. Phobos offers strategic advantages. The doom awaiting Phobos adds a certain urgency to any plans for utilizing the inner moon as a base or resource. The knowledge that this world has only 50 million years remaining before destruction arriving eventually, even if not soon, by human timescales. 50 million years is an enormously long time by any human measure, longer than our species has existed in anything like its current form. Plenty of time for whatever future awaits humanity. The doom is certain but distant, allowing planning horizons measured in millions of years if we somehow endure long enough to need them. The urgency is relative. Deimos offers a different kind of resource, one that will remain available essentially indefinitely for whatever purposes future generations might imagine for a small, dark moon orbiting far from Mars in stable configuration. The outer moon's patient orbit means it will still be there billions of years from now, unchanged in any significant way, available for observation, study, and possible utilization as long as Mars exists as a planet. The permanence of Deimos contrasts with the temporary nature of Phobos in ways that might influence decisions about which moon to prioritize for human activity. Stability has value. The samples that future missions will return from Phobos may revolutionize our understanding of where these moons came from and what they are made of at levels of detail impossible to achieve through remote observation alone. Laboratory analysis using the most sophisticated instruments available on Earth will extract information about composition, age, and history that remains hidden from spacecraft instruments limited by power, weight, and complexity constraints. The samples will speak directly about questions that orbiting instruments can only address indirectly through inferences and models. Direct evidence matters. The Martian moon's exploration mission, planned by Japan, represents the most ambitious current effort to collect and return these samples. With launch targeted for the middle of this decade and sample return expected several years after that, the spacecraft will land on Phobos, collect material from the regolith covering the surface, and bring that material back to Earth using techniques developed through decades of experience with sample return missions elsewhere in the solar system. Success would provide answers long sought by planetary scientists. Other nations and organizations have proposed missions to Mars's moons as well, reflecting the growing recognition that these small bodies offer scientific value disproportionate to their modest sizes and unassuming appearances in the night sky. The questions they can answer about early solar system processes, moon formation mechanisms, and the history of the Mars system justify the effort and expense required to reach them across the gulf of interplanetary space. The moons have become targets. The relationship between Mars and its moons will continue essentially unchanged for longer than human civilization has existed, longer than our species has walked the Earth, longer than most of the time since complex life first appeared in the ancient oceans of our home world. Phobos will continue racing around its close orbit, while Deimos continues its slow patrol farther out. Both moons maintaining their ancient paths through the darkness near the red planet that holds them gravitationally. The constancy is remarkable. Yet change will come eventually, written in the orbital mechanics that govern the long-term evolution of both moons, through processes operating on timescales far beyond human experience, or planning horizons. Phobos spirals inward, Deimos spirals outward, and the Mars system will look different in the distant future than it looks today when viewed from sufficient temporal distance. The physics permits no other outcome than the one already determined by the current orbital parameters of both small moons circling Mars together. For now, in the present, that we actually experience and can study directly, both moons continue their ancient patterns around the red planet that has held them close since the early solar system, when their orbits were established. The surface of Mars shows the marks of this long relationship. Impact craters created by debris from the moons, and possibly future ring material from Phobos waiting to fall. Moon and planet are linked through gravity and history. The exploration of these moons through words and imagination approaches its conclusion as we prepare to step back and consider what we have learned through our journey tonight through the Mars system. Phobos and Deimos have revealed themselves as strange and fascinating worlds, small and dark, but full of stories waiting to be told through closer examination than we have yet achieved. Their presence makes Mars more interesting than it would be alone, two companions adding complexity and motion to the sky above the cold red deserts below. The journey draws toward its end. The two moons of Mars have kept their patient vigil around the red planet for longer than life has existed on Earth in any complex form recognizable to modern observers. They have circled in their separate orbits since the early days of the solar system, when the configuration of planets and moons was first being established through processes of accretion and capture. Phobos and Deimos are ancient in ways that dwarf all human experience of time and duration, patient beyond our ability to truly comprehend the meaning of such endurance. They were there before us and will remain long after. They are strange companions by any standard, small and dark and irregular, where we might expect round and bright if we imagined moons based only on our experience with Earth's substantial lunar companion. Mars chose its moons differently than Earth chose its moon, ending up with two humble attendants rather than one grand satellite that might compete for attention against the distinctive character of the red planet itself. The moons fit Mars in some way that feels appropriate, even if we cannot articulate exactly why the match seems right. Perhaps chose is the wrong word, since Mars did not select these moons through any intentional process, but rather acquired them through gravitational capture or impact formation, mechanisms that operated according to physics rather than preference. The processes occurred billions of years before any mind existed to have preferences about moons or to notice the difference between one arrangement and another. Yet the result feels somehow fitting, the small dark moons accompanying the small red planet through its orbit around the Sun. Phobos has revealed itself through our exploration as a world of dramatic features, despite its modest size and humble appearance when viewed from great distances across the solar system. The enormous Stickney crater nearly shattered this moon when it formed, leaving a scar that dominates nearly 1/3 of the entire surface area, visible from any angle of approach. The mysterious grooves cross the terrain in patterns that may mark the moon's ongoing destruction, cracks forming as tidal forces slowly pull Phobos apart, while it spirals inward toward doom. The close orbit sends Phobos racing backwards across the Martian sky 3 times each day. The fate of Phobos is written in orbital mechanics, the physics of its situation allowing no escape from the eventual crossing of the Roche limit. where tidal forces will exceed structural strength. In approximately 50 million years, the Moon will either crash directly into Mars or break apart into fragments that will form a temporary ring before raining down onto the Martian surface below. The timeline is certain, even if the exact outcome remains debatable. Destruction inevitable on timescales that seem impossibly long to human minds, yet represent mere moments in the lifetime of the solar system. Phobos is temporary. Deimos has shown us a gentler character through our examination of its softened surface and patient orbital motion around Mars in its distant stable path through the darkness. The thick regolith covering everything has rounded the craters into shapes almost peaceful compared to the sharp-edged impacts visible on more active worlds throughout the solar system. The orbit slowly expands rather than contracting toward destruction. The future of Deimos measured in billions of years rather than mere tens of millions, like its larger sibling. The difference could not be more complete. Together, the two moons create something unique in the solar system. A planet with companions so different in character and fate, yet sharing the same dark coloring and probable origin in processes still not fully understood. One moon races and one moon dawdles. One moon scars and one moon softens. One moon dies and one moon endures, yet both orbit the same planet in the same general region of space around the Sun. The contrast defines them. The view from Mars reveals both moons as active participants in the planet's sky, creating patterns that future human residents will come to know as intimately as we know the phases of Earth's moon today. Phobos racing backward across the darkness multiple times per day, while Deimos barely seems to move at all, both visible simultaneously during portions of each night in the Martian sky above. The dynamic will become familiar to those who live beneath it. Those future observers will watch Phobos transit the Sun in its quick 30-second passages, the irregular silhouette crossing the solar disk, in events already photographed by rovers currently operating on the Martian surface. They will note the position of Deimos, barely changed from night to night, despite the hours that pass between observations of this slow outer moon. They will come to understand the orbital mechanics that determine why one moon moves one way while the other moves differently through their shared sky above. The moons will become landmarks and references for generations of Martian residents, their positions and phases marking time in ways we can only begin to imagine from our current vantage point on Earth, watching from afar. The strangeness will fade as familiarity grows, the alien sky becoming home sky for those who live beneath it permanently and have never known any other arrangement of moons above their heads at night. Normal adjusts to circumstance. The samples that will eventually return to Earth from Phobos will answer questions that have persisted since Hall first spotted these moons nearly 150 years ago through his telescope in Washington, D.C. The composition and age and history locked in those rocks will speak across the gulf of interplanetary space, bringing direct evidence of what these moons are made of and where they originally came from in the ancient solar system. Understanding will deepen. For now, Phobos and Deimos continue their orbits as they have for billions of years, patient in ways that only objects without consciousness can be patient through the vast stretches of time that separate one event from another in the slow evolution of planetary systems. They are present in the Martian sky whether anyone watches them or not, maintaining their paths through darkness that has never known interruption since their orbits were established so long ago. The vigil continues. The darkness of their surfaces absorbs most light that strikes them, giving both moons a modest quality that seems almost humble compared to the bright, icy moons orbiting Jupiter and Saturn in the outer solar system, far from Earth. They do not demand attention through dramatic brightness or spectacular features visible across interplanetary distances, content to circle Mars without advertising their presence too loudly through the darkness of space. Modesty characterizes them, yet they have commanded attention through their strangeness. Their irregular shapes and unusual orbits and mysterious origins, drawing scientific curiosity across the centuries since Hall first spotted them and began the process of understanding that continues to this day in observatories and laboratories worldwide. The questions they raise remain partially unanswered, invitations to deeper investigation that future missions will undertake in the coming decades of solar system exploration from Earth. Mars keeps its two small companions close, and they in turn make the Martian sky unlike any other in the solar system, where moons can be observed from solid surfaces beneath breathable skies. Two moons following different rules, moving at different speeds, facing different fates, yet sharing the same planet and the same ancient history that brought them both to orbit, the red world that holds them still gravitationally. The relationship endures. The night continues around Mars as it has for billions of years. Phobos racing through its latest orbit, while Deimos creeps slowly along its more distant path through the darkness above the cold red deserts below. Both moons remain present and patient above the rusty surface that may someday welcome human observers who will look up and see what we have explored tonight together. They are strange moons, dark and small, and battered by time and gravity. But they are Mars's own moons, and they will continue their vigil for as long as physics allows.